Hey guys, we'll do lesson 2 together right now. If at any point during the stream here, if it starts to lag, let me know so I can try and fix it for you guys. So hopefully you've got lesson 2 ready to go. Hey Kareem, hey Kevin. And we'll start just by looking at some terminology you're going to need for the rest of the unit. So in this unit, we're going to be talking a lot about average rates of change and instantaneous rates of change. This lesson's all about average rates of change. So our first definition is, what is a rate of change? So a rate of change, you learned back in grade 9 that a rate of change is the change in y, so the change in the dependent variable, with respect to the change in x, the independent variable. And we can calculate that rate of change using your slope formula. Rise over run, change in y over change in x. The next definitions you need are definitions for secant line and tangent line. You're probably familiar with what those are, and there's a diagram over here that shows you what they are. A secant line is a line that passes through 2 points on the graph of a function. So notice that the secant line passes through those 2 points. So that's a secant line. A tangent line, on the other hand, only passes through 1 point on a function. Or I shouldn't say passes through, it just touches the function at a single point within a given interval. So this red line right here is a tangent line because within a given interval, so if I just look at this little interval right here, it only touches the function at 1 point within that interval. So we would call that a tangent line. Now we need to distinguish between those two because each of those represent different things. An average rate of change takes place over an interval, and we can calculate the average rate of change by finding the slope of a secant. But an instantaneous rate of change, it takes place in an instant at a single point. So if we want to calculate an instantaneous rate of change, we actually need to know a slope of a tangent. And this may seem a little contradictory to you to think of an instantaneous rate of change, right? How can something be changing in an instant? When we calculate a rate of change, we do change in y over change in x. Or if we think about it as velocity, remember when calculating velocity, you do change in distance over change in time. So how do we calculate, let's say, an instantaneous velocity? How do we know when you're driving a car how fast you're going at any one given instant? How does your car know how fast you're going at an exact moment in time? If we wanted to calculate how fast you're going at an exact instant, well, what's the change in time at a single point in time? It's 0. And what's your change in distance at a single point in time? 0. So how do we evaluate an instantaneous rate of change when logically it should give us 0 over 0, which is undefined? Yes, this has a lot to do with physics, Natalie. The concepts behind it for sure, but this is all going to lead to something called finding the derivative of a function, and that's what you're going to do a lot in calculus. But what we need to do is understand the concept behind an instantaneous rate of change and how it's actually something difficult to calculate. If we wanted to figure out the instantaneous rate of change of this function at that point right there, we would need to know the slope of its tangent line, and finding the slope of that tangent line is actually difficult to do, and there's a few concepts we're going to have to learn before we do that. So this lesson, we're not going to look at instantaneous rates of change. I was just kind of giving you an intro to try and think about it as we go through this lesson. What we're going to be focusing on in this lesson is just average rates of change, slopes of secant lines. So an average rate of change corresponds to the slope of a secant line between 2 points on a curve. So if we have a function and we want to figure out what's the average rate of change between 2 points, let's say this point and this point, we can find that average rate of change just by finding the slope of the secant line that connects them. And we all know how to find slopes of lines. It's just change in y over change in x. And after we learn how to find slopes of secant lines, the rest of the unit is going to be on finding slopes of tangent lines. So here's just a diagram that reminds you about slope formula. So if we're finding average rates of change, we're just finding the slope of a line that connects 2 points. Each of those points have an x and a y coordinate. We pick one of those points to be our first point and one of them to be the second. It doesn't matter which one is which. And then to find the slope of the line between those 2 points, we just do the change in the y values, so y2 minus y1, over the change in the x values, x2 minus x1. So that's where this formula comes from here. Last little page of definitions before we actually do an example. I have a graph here of a linear relationship. So when you were introduced to rates of change back in grade 9, you were always working with linear relationships. And if we were, so first blank here is linear. If we were to look at this linear relationship, you learned in grade 9 that if we wanted the slope of that line, so the rate of change, you could use any pair of points on that line. You could find the slope between those 2 points or the slope between those 2 points. It wouldn't matter. It would all be equivalent. Linear relationships have a constant rate of change. So average rates of change calculations over different intervals, if you have a linear relationship, all give you the exact same result. So that's why when you were doing slope in grade 9, it didn't matter which 2 points you picked. But in this course, we're going to be focusing on nonlinear relationships. So let me just draw a graph on here. Let's say we had a relationship that looked like this. Depending on which pair of points I found the average rate of change between, so if I found the average rate of change between these 2 points, so the slope of that secant line, or the average rate of change between these 2 points, so that secant line, I would clearly get different results for the slope of those secant lines. So the average rates of change are different depending on what interval of x values you choose. So that's all this says here. It says nonlinear relationships do not have a constant rate of change. Average rates of change calculations over different intervals of the independent variable give us different results. So if it's a linear relationship, you would get the same result no matter what interval of x values you were finding the rate of change between. But nonlinear relationships, you would get different secant slopes depending on the interval of x values you're finding the secant slope between. Okay, maybe let's get into an example now so you can see what we're actually going to do. So this example says there's Andrew, he's draining water from a hot tub. So we've got a hot tub that holds 1,600 liters of water, and it takes 2 hours for the water to drain completely. The volume, V, in liters of water remaining in the tub at various times, T, in minutes, is shown in the table and graph. So we have a table of information about the amount of water in the hot tub based on the time that it's been draining for, and we also have the graph of all of those points plotted. Part A says calculate the average rate of change in volume during each of the following time intervals. So we're looking for the rate of change of volume with respect to time. And the symbol for rate of change is m when we're doing average rates of change. So we're trying to calculate the rate of change of volume with respect to time. So we would do change in volume over change in time. For part A, it wants between those time intervals. So what's the average rate of change between a time of 30 and a time of 90? So let's look over to the table and look at what we know about at those 2 times. So at a time of 30, there's 900 liters of water in the hot tub, and at a time of 90, there's 100 liters of water in the hot tub. So it lost 800 liters in 60 minutes. So all we have to do is do our change in volume over change in time formula, and we can get the rate of change. Graphically, what are we finding? Well, where's the point when time is 30? It's right here. And where's the point when time is 90? Are we doing 90 or 60? Yeah, 90. When time is 90 is right here. So graphically, what we're trying to do is find the slope of the secant line that connects those 2 points. So we're trying to find the slope of that secant line. And to find the slope of that secant line, all we need to do is our rise divided by our run. So we need our change in volume divided by our change in time. We're going to use a slightly new notation for it, and that's going to be the important part of this lesson. Instead of calling it y2 minus y1 over x2 minus x1, we're going to use function notation. So this point right here, this volume, this is the volume when time is 30. So I could call this v at 30. That's the volume at 30. That's the y value when x is 30. Or in this case, that's the volume when t is 30. And this y value, I could call that v at 90. That's the volume when time is 90. So this is going to be the important part of this lesson, is using this new function notation. So when I calculate my slope, my rate of change, I need to use these values, or these notations, instead of y2 minus y1. So instead of calling these y2 and y1, and then in my quotient writing y2 minus y1, I'm going to write v at 90 minus v at 30. So in our formula over here, when we do change in volume, we're going to do the volume at 90 minus the volume at 30. And you could do it the other way around. You could do v at 30 minus v at 90. It doesn't matter, just as long as then when you do your difference in times, the order matches. So since I did the volume at 90 minus the volume at 30, now when I find the difference in times, I have to do the same order. I would have to consider this one my second x value, this one my first. So I'd have to do 90 minus 30. So my change in time, 90 minus 30. So notice that the order matches up. V at 90 minus v at 30 over 90 minus 30. We could equivalently do v at 30 minus v at 90 over 30 minus 90. It would give you the same answer. But now that we have this new notation of writing an average rate of change, we can calculate it. So our volume at 90 from the table was 100. So I can replace v at 90 with 100. And my volume at 30 minutes was 900. So I can replace v at 30 with 900. And this is all over 60. And then we need to just evaluate this. It's negative 800 over 60. And then for that we get negative 13.3. And we should figure out what units were in here. So graphically we figured out the slope of the line is negative 13.3 over 1. Rise negative 13.3, so that means go down negative 13.3 over 1. That's the slope of this line. What we want to do is figure out the units we are in. So our y value is volume in liters, and our x value is time in minutes. So we did change in volume over change in time, so we did liters divided by minutes. So our rate of change is in liters per minute. So that tells us that the hot tub is losing about 13.3 liters every minute. And that makes sense because he's draining the water out of the hot tub. Let's now find a couple more average rates of change with this same information. So part 2 asks us to find the average rate of change between 60 and 90. Let's look back at the graph and the table. So let me just clear everything that I've drawn here. Okay, so this time we're finding the average rate of change between 60 and 90. So between those two. Notice this line is slightly less steep than the blue one. So the slope of that line is less steep, so when we calculate our average rate of change, we would expect to get a number closer to 0, a smaller absolute value. So it was losing 13.3 liters per minute over the first interval. Over the second interval, it's probably losing slightly less liters per minute. But let's do the calculation. So if we're trying to find the slope of that red secant line, I'm using these 2 points. I'm using at 60 minutes and at 90 minutes. And this value right here, remember in our new notation, that's the volume at 60, and this is the volume at 90. So when I do my change in volume, I'll do V at 90 minus V at 60. And when I do my change in time, I'll do 90 minus 60. So let's set that up. So the volume, or sorry, the rate of change, which is represented with m when it's an average rate of change, is change in volume over change in time for this example. And we want the rate of change between 60 minutes and 90 minutes. So I'll do the volume at 90 minus the volume at 60. And this is all over 90 minus 60. And then we can just sub in from the table of values, the proper values for V at 90 and V at 60. So V at 90 I know is 100. And let me look back to figure out what the volume at 60 minutes was. The volume at 60 minutes was 400. And this is over 30, so I have negative 300 over 30. So that's just negative 10 liters per minute. So it's losing slightly fewer liters per minute over that next interval. So notice it's not a constant rate of change. The water isn't draining at a constant rate. It's a nonlinear relationship. I have 2 more intervals I wanted you to try. I think doing 1 more of those 2 would be enough, because it may be a little repetitive to do 4 examples of the same thing. Let's just do the last interval between 110 and 120. So let's look back at our graph. So let's do between 110 and 120. Okay, that's these 2 points right. Let me clear this ink first, actually. Alright, so the last interval is between this point and this point. Notice that secant slope is not steep at all, so the water's draining even more slowly here. Let's see if I can draw a small secant line there for you. There we go. We're finding the slope of that small secant line there. Hopefully you can see it. So between 110 and 120, so I'm doing these 2 points. This y value is the volume at 110 minutes, and this y value is the volume at 120 minutes. So when I find the rate of change, the change in volume over change in time, I'll do V at 120 minus V at 110 over 120 minus 110. So the average rate of change would equal the volume at 120 minus the volume at 110 over the change in time, 120 minus 110. And let's get our volumes. They were 0 and 10. So 0 minus 10 over 10. That's negative 10 over 10, which is negative 1 liters per minute. So it's only losing 1 liter per minute over that interval on average. So notice the average rate of change over each of those 3 intervals we calculated, and we'll skip part 3. You could do it if you wanted to, but I think it was getting a little repetitive. The average rate of change over the 3 intervals were all different because it was a nonlinear relationship. Over the first interval, it was negative 13.3 liters per minute. Over the next interval, it was negative 10 liters per minute. And over the last interval, it was negative 1 liters per minute. So that rate of change was decreasing. So does the part B just says, does the tub drain at a constant rate? You don't have to write all of this, but the important thing here is the tub does not drain at a constant rate. This is because it's a nonlinear relationship. And then I just have a little physics reasoning at the end as to why that's happening. So if you think about, there's 1,600 liters of water in that tub at the beginning. So that's putting a lot of pressure to get the water out. So the rate, as the water drains, the weight of the water is causing less pressure, pushing the water out. So that's why the rate slows as the water empties, because the pressure from the weight of the water is decreasing as there's less water in the hot tub. But the only important thing I want you to make sure you write down here is that it does not drain at a constant rate. Sorry, I should have circled does not drain at a constant rate because it's a nonlinear relationship. So we got 3 different average rates of change, so we know it's a nonlinear relationship. And we could see that from the graph. So if you have any questions with how we did this from a graph or a table, make sure just put them in the chat so I can answer them for you guys. And all we have left to do is the same type of question, but just do it from an equation. So we're not going to have a table or a graph, we're just going to do it from an equation. So let's give that a shot. Oh, I had a couple blanks here for you. This is just the difference between a positive and negative rate of change. So all 3 rate of changes we got in that first example were all negative. And they were all negative because the amount of water was decreasing as time was increasing. So a negative rate of change indicates the quantity of the dependent variable, so in our example it was volume, was decreasing over the interval. So the secant lines all had negative slopes. Positive rates of change would indicate that the dependent variable would be increasing over an interval, and you would see the secant line would have a positive slope. Okay, so this is what I was talking about next. We're going to do the same type of question, but we're only given the equation. So it says someone tosses a rock upward from a cliff that's 120 meters above the water. The height of the rock above the water is modeled by this equation. So we don't have the graph. I'll show you the graph just so you can understand what we're doing, but we don't have the graph this time, where h is the height in meters and t is the time in seconds. Calculate the average rate of change in height during each time interval. So let me just give you a rough idea about what this graph looks like. We've got a quadratic, and it tells us someone is standing on a cliff, and they toss the rock up. So the cliff is 120 meters high, so it's going to start at 120. They're going to toss the rock up, and then of course gravity is going to pull the rock down. So our function is going to look something like that. It's a nonlinear function. It's a quadratic. We need to find the average rate of change of the height of the rock with respect to time over 3 different intervals. So when we find the average rate of change between 0 seconds and 1 second, I should also, sometimes questions will be written instead of with inequalities, they'll be written in interval notation. So you'll see it written like this, 0, 1 in square brackets. It means the same thing. So if you see it written like this, know that that is the time interval. That's the interval of independent variables. So that's the interval of times for this question. So if we want the average rate of change between 0 seconds and 1 second for the height, we'd say m equals the height at 1 minus the height at 0 all over 1 minus 0. That's our change in height. So up here, this is just our change in height. It's our change in y. And this is our change in time, our change in x. So we're just doing change in height over change in time again. But how do we get h at 1? We don't actually have a table of values. We would actually have to plug 1 in for these t values and solve for the height. So if I were to do that, if I were to plug 1 in for those t values, I would get... Oh, Faith, no, you won't have round brackets. It'll always be square. If it was round, it actually wouldn't affect this question, but they'll always be square. So when I plug 1 in, I would get negative 5 times 1 squared. That's just negative 5. Plus 10 times 1. So that's 10. So I've got negative 5 plus 10. That's 5. Plus 120. That's 125. So h at 1 is 125. Minus h at 0. We'll plug in 0 for those t's. I would get 0 plus 120. That's 120. And that matches the graph I showed you here, right? Here was the height, and here is the time. At a time of 0, the height was 120, because that's how tall the cliff was. But we just verified that by plugging it in. And this is all over 1 minus 0. And we get 5 over 1. That's 5 meters per second. I think it said our height was in meters and our time was in seconds. Height in meters, time in seconds. So yes, we found the rate of change of height with respect to time. So it's in meters per second. So we found over the first interval between there and there, between 0 seconds and 1 second, the height of the rock is actually increasing by 5 meters every second on average in that interval. Maybe it's increasing faster at the beginning of the interval and slower at the end of the interval, but that's what it's changing by on average in that interval. Let's look over at the graph of the function. So here's the graph. I made this in Desmos for you. So what we did, we found the slope of this secant line, this purple secant line right here. So notice it's a nonlinear relationship. So like I was saying, at the beginning of that interval between 0 and 1, the slope of the function was a little steeper than near the end, but on average, the slope of the secant line tells us the average rate of change between those 2 points. So we found the average rate of change between that point and that point. And notice this point is actually right at the vertex. That's going to be useful when doing the second part of this question. So the second interval for this question is between 1 and 2. So let's look back at this graph. We're now finding the slope of this secant line between that point and that point. Notice the purple secant line was an interval 1 unit before the vertex, and the green secant line is the interval 1 unit after the vertex. And we know parabolas are symmetrical, so we should probably be able to predict what we're going to get for the slope of that green line compared to the slope of that purple line. It's going to be the same rate of change, but negative, because parabolas are symmetrical. But let's do it algebraically to figure it out. So between 1 second and 2 seconds, the average rate of change would equal our change in height divided by our change in time. So h at 2 minus h at 1 all over the change in time, 2 minus 1. So up here is our change in height, down here is our change in time. And now we need to calculate what is the height at 2 and what is the height at 1. So let me go back to the equation and calculate those. So the height at 1 we've already calculated, it's 125. But what's the height at 2? If I plug 2 in for these t's, negative 5 times 2 squared, so that would give me negative 20, plus 10 times 2, so that would be 20. So negative 20 plus 20, oh, that's 0, plus 120, that's 120. So over here, my height at 2 is 120, and my height at 1 was 125, and this is all over 1. So I get negative 5 meters per second. Like I said, it has the same absolute value as part A, but it's negative. So that means the height of the rock is now decreasing by 5 meters per second on average over that interval. Let's try our last interval. Our last interval says between 2 seconds and 3 seconds. So in a question it may be written like this. Just make sure you know that is the interval of x values, or in this case the interval of t values. When we calculate it, we need to do our change in height over change in time. So height. Height at 3 minus height at 2 over 3 minus 2. Oh, and I haven't mentioned it much, but remember, it doesn't have to be that order. We could have done h at 2 minus h at 3 if in the denominator we then did 2 minus 3. It would be equivalent. We would get the same answer. Okay, let's calculate h at 3 and h at 2. Well, I know h at 2. H at 2 is 120. Now I just need to figure out what's h at 3. So if I plug 3 in for these t values, so plug 3 in for each of these, negative 5 times 3 squared, well, that's negative 5 times 9, so that's negative 45, plus 10 times 3, so that's 30. So I have negative 45 plus 30, that's negative 15, plus 120, that's 105. So I have 105. 105 minus 120 divided by 1, that's negative 15 meters per second. So the rock is falling even faster now. It's falling at a rate of 15 meters per second on average over that interval. And that's due to the acceleration of gravity. Gravity is accelerating at a rate of 9.8 meters per second squared. So, of course, because of gravity, it's going to keep falling faster and faster and faster. So I think that's it. Oh, and let me just show you that graph in Desmos quick. So the last interval we found, I'll have to zoom out for this one. The last interval we found was this blue interval here. And notice how this line is now steeper than the green line, which indicates it's now falling faster. So we found the slope between that point and that point. So I think that's it for the lesson. That's all there is to average rates of change. The only real new thing in this lesson was getting used to this function notation for when we're doing our change in our y values, our change in our dependent variables. So just give the practice questions a shot. It'll be quick. It's just a bunch of average rates of change calculations. And I'll talk to you guys tomorrow. So have a good rest of the day, everyone.